Okay, so in this question, we're given a sphere, and it's asking us to figure out which of the following statements are true. So looking at all of the statements here, it deals with like intersecting a plane of some sort. So that's all that. So we just have to worry about like whether or not a plane actually crosses through a sphere. We don't have to focus on like anything else that like any of the other conceptual stuff for a sphere. So that's kind of nice. So the first thing I'm going to do is I'm going to write out the general formula for a sphere because that's going to be important for later down the line. So recall that with a sphere, like we know that that could be equal to like x squared plus y squared plus z squared is equal to r squared. And where r that would be like a radius. The problem with this formula is that this formula is it's going to give you a sphere that's centered at the origin of a three-dimensional space. If you wanted to shift it and have that sphere be like somewhere else on in your space, you'd need to add like a shifting value to each of these x, y, and z terms, and so we'd end up with a more generalized formula for a sphere. That is this, where we have that x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. So these a, b, and c values are what's going to allow us to shift our sphere and have it be centered somewhere else on the plane. So applying that to the given sphere here, we see that we'd have an a value of 1, a b value of 2, and a c value of negative 4. It's negative because we have a positive here, so like this sign was flipped with a negative number. And then we can see here that we have a 9 here, and that would be equal to like our r squared value. So from there, we can deduce that the radius should be the square root of 9, so 3, and it would be centered at 1, 2, and negative 4. So let me write that over here. So the center is at 1, 2, and negative 4, and the radius is the square root of 9, which is equal to 3. And so now this is all we need to figure out whether or not a plane intersects our sphere. So the next thing I'm going to do is I'm going to draw a two-dimensional plane with a circle on it, and then what we get from there, I'm going to extend that to 3 dimensions, and to make it make more sense. So we have a two-dimensional plane here, where this is our x-axis and this is our y-axis, and then let's say we just have like a sphere here, or no, like a circle here, and its center is like somewhere around here, and it has a radius of r. Looking at this just from a visual inspection, you can pretty obviously see that the x-axis is intersecting the circle here, because well, this line is just going straight through the circle. But mathematically speaking, what you'll notice is that what that means is like, well, yeah, visually it's just intersecting, but you'll notice that the distance from the axis to the center of our circle is less than the radius of the circle. So with that we can come up with a condition, that being that in order for a axis or plane to intersect a circle or sphere, the distance from that line, or like a plane or axis, would have to be less than or equal to the radius of the sphere. So that would be our win condition for this question. So let me write that out here. Distance from like a axis slash plane has to be less than or equal to radius. So now we can extend this to 3 dimensions. So like on a 3-dimensional plane, with like, let's say we had like a plane here, and then let's say we had like a sphere here, and then like it's like, and then let me put like a center here with another radius. You can see how this plane would intersect the sphere if the distance is less than or equal to the radius. It's not the best drawing, but I hope you can kind of see my point with that. So now we can start, and so now from here we can use that information to figure out whether or not the planes of a 3-dimensional space are going to intersect with our circle here. So the next thing I'm going to do is I'm going to draw a better 3-dimensional plane. Or actually, no, I don't think we have to do. I think this drawing could kind of illustrates my point as well as this one pretty well. Um, so we have a center here of 1, 2, and -4. And we know that an xy on an xy plane, so an xy plane, that corresponds to a z coordinate being equal to 0. A yz plane, that corresponds to a x coordinate being equal to 0. And then a zx plane, or an xz plane, that corresponds to y being 0. And the reason for that is you can use the same logic as a two-dimensional plane where you have like the y-axis. If you're on the y-axis, that means that your x-coordinate is equal to 0. If you're on the x-axis, that means your y-coordinate is equal to 0. So in 3 dimensions, whatever coordinate isn't in the name, that's going to be what's equal to 0. And so that's what we're going to, and so that's going to tell us which part of this coordinate to focus on for each of the planes. So starting with the xy plane, that means that z is equal to 0. That means we'd have to focus on the z coordinate of our circle. And so we can see that the point z, z in this case is equal to -4, which means that the distance from the plane is going to be equal to 4. And 4 is greater than our radius, so which is 3. So we know that radius equals 3. So it needs to be, the plane needs to be, it needs to be less than or equal to r, and 4 is greater than r. So we know that the xy plane does not intersect with the sphere. And then here on the yz plane, now we can focus on x. We know that x in this case is equal to 1, and so x equals to 1, so distance equals 1, which is less than r. So in this case, the yz plane does intersect. And then looking at the last case of xz plane, now we're going to focus on the y coordinate. So in that case, y is equal to 2, which means the distance from the plane is equal to 2, which is also less than r. So from here we can conclude that the yz plane and the xz plane do intersect with our sphere, but the xy plane doesn't. So matching that up with our answer choices, that would mean that the answer would be D. Alright, so in this question we're given a cubic tank whose sides are 1 meter long, and it sits on the ground and is filled with a liquid of density 100 kilograms per cubic meter. It's telling us to assume gravitational acceleration, g, is equal to 10 meters per second squared, and it's asking us to compute the total force on one of its side walls due to pressure. So 2 big things I want to focus on in this question is going to be total force and side walls due to pressure. So I'll keep those underlined for the entire thing, because these are going to be these two key phrases are going to be very important in giving us an answer. So I mean, obviously, first off, it's asking us to find a total force, and all of the answers are in newtons. So we're going to have to come up with a force by the end of this entire question. And so, but it also mentions pressure in the question. So the 2 things you might be focusing on would be, I guess, a force and a pressure. And so the first thing that you might be thinking is maybe figure out a way to relate the formulas for those 2 things. So like we know that generally speaking, F equals ma, and then pressure is equal to rho gh, right? And so you might be thinking figure out a way to relate these 2 things and come up with an answer for F. But for this question, what I'm actually going to do is we don't even have to focus on F here, because what we can do is we can actually squeeze out a force from the pressure by focusing on what pressure actually is conceptually. So in reality, we're only going to be working with this formula. We're going to be messing with that and tweaking that, and we'll be able to get a force. And you might be wondering how we can do that, because pressure is not force. Like, we know that the units for pressure would be like a Pascal, and the units for force are generally Newton, right? But a Pascal and a Newton are not the same thing. But they are related. Even though they're not the same thing, they are related. And you can figure this out by looking at what a Pascal or a pressure actually is. So pressure, in reality, that's actually going to be force over some sort of area. And we know that the general units for force are Newton, so N. And then we know that area, that would, like a general unit, would be like square meters. So in reality, a Pascal is going to be equal to newtons per meter squared. And so looking at this, you can see that there is a newton or a force in a pressure. And so we can use that information to isolate a force from that. And so that's why we only have to use this equation. And so now the thing we have to do is figure out how to get rid of this meter squared so that we just have a newton. And so the way to do that is actually in the way this question is set up. So going back to the total force part of this question, that tells us that it's asking us to find the total force in our cubic tank. So let me draw out a diagram here. It'll to make things make more sense. Since we're dealing with a tank here, oh wait, and yeah, we have our 1 meter here. Anyway, since we're dealing with a tank here, that it's not like say like in like E&M physics, it's not like a point charge. It's like it has mass. It has like stuff going on. So what I mean by that is the pressure is not going to be the same throughout the entire tank. It's going to be different depending on where in the tank you are. Because if you look at it logically, like the bottom of the tank, that's going to have more pressure than the top of the tank, because at the bottom of the tank you have like all the liquid piling up on top of you and so squishing you. Whereas at the top of the tank you're on top of the liquid, so you're not being squished by the liquid. So the pressure at the top is going to be less than the pressure at the bottom, giving us a non-uniform pressure, which also means that the pressure is going to be different depending on where along this height you're going to be. And so what we're going to have to do is we're going to actually have to take an integral as well, because we're going to have to sum up all of the possible pressures along this height. So in reality, for this question, height is not going to be constant, it's going to be a variable. And so we're going to have to attach a differential to this formula. But the cool thing is that right there is how we're going to get rid of this meter squared. So bringing this down here, we're going to have to rewrite this as P is equal to rho g h times some differential, where A, that's going to be an area. So, and we know that an area, generally speaking, the units for that is a meter squared. So this differential is going to have the units meter squared. So I'll put that here. So this is going to be meter squared. And so in reality, the units for this new equation that we came up with, that's going to be equal to newtons per meter squared times meter squared. And that will allow us to cancel out these meters squared, and we'll end up with just a newton after we set up the rest of this equation and simplify it. So since we attached a differential here, we need to figure out a variable, and then let me rephrase. Since we attached a differential here, and I mentioned earlier that h is going to be a variable because we're going to be focusing on different heights throughout this 1 meter thing, we can replace h with a variable, and we can replace this differential with like a differential with respect to that variable. So I'm going to use the variable y because we're working like vertically here. And so in reality, we can rewrite this as P is equal to rho g times some integral y with respect to y. And so all we have to do from here is figure out what our boundaries are going to be, because and then since actually no, let me rephrase. Figuring out the boundaries from here is going to be pretty straightforward, because the lowest possible place that the height can be would be the bottom of the tank, and the highest possible height would be the top of the tank. And we know that the total height is 1 meter, so that would mean that the top of the tank would be 1 and the bottom of the tank would be 0. And so from here, all we have to do is plug in our given values for rho and g, and then simplify this entire thing, and we'll have an answer. So when you do that, you'll end up with rho, that being recall rho is density, so that would be 100 kilograms. So you'd end up with, did I just X out? Give me a second. Oh, no, we're good. I just mistapped. Anyway, yeah, so rho, that's going to be 100 times g, so which is given to us as 10, times our integral from 0 to 1, y dy. All we have to do from here is just simplify, so you'd end up with 1,000 times y squared over 2, evaluated from 0 to 1. simplifying again, you end up with 1,000 times 1/2 squared minus 0. Yeah, so 0 squared over 2, which simplifies again to just 1,000 times 1/2 minus 0, which just simplifies to 500. And then since we mentioned earlier here how with this relation you end up with just a Newton, all we have to do is just attach a Newton here, and we have our answer to this question. So the answer to this question would be 500 newtons. So let me write that here. And so the answer to this question, matching up with our answer choices, would be B. All right, find the area of the region enclosed by x is equal to y squared and x is equal to 8 minus y squared. Oh wow, there's some trickery, some tomfoolery going on in this question. Notice how these functions are written where x is equal to some sort of garbage instead of y is equal to some sort of crap. That's going to change up the way this function is going to graph, because out of force of habit, like you might be just super used to functions where you have like y is equal to something, and so you'd end up with like, I don't know, maybe two functions. Like it might be easy to think that it's going to end up looking like this, where you have like two functions like you'd end up with a parabola that looks like this and another one that looks like that, like in a normal case, right? Oh wait, come on, I'm trying to get the right colored pen, like this or something, and then you just integrate this, find this area, and call it a day. But the problem is, since the variables are flipped, this is actually going to look like this. These two graphs are actually going to end up looking something like this, where you have like you have one sideways parabola like this, and another sideways parabola looking like this. And so if you try to integrate this with respect to x, you're gonna have to take some preliminary steps first, and the computation is gonna be like really, really bad and like really ugly and painful. But that might be more intuitive to you. So if you want to do it that way, you can. Just there's gonna be more room for error. So I would highly suggest for questions like this being comfortable with integrating vertically, like integrating along the y-axis instead of the x-axis. Like computationally it's identical, it's just that visually it might not be as intuitive because you're looking at it sideways. And so I'll show both approaches. So the first approach, integrating vertically with along the y-axis, if you do it that way, you can keep these functions as is, and then integrate it. And if you really want to, you can just pretend that the variables are flipped. Just yeah. Anyway, yeah. I'll show the first approach of just keeping the functions as is. So we have x is equal to y squared here, and x is equal to 8 minus y squared here. We need to find the boundaries because they're not given to us here. Like this isn't like your walk in the park area under the curve question where they give you the boundaries. We're gonna have to find them ourselves. And the way we find that is, well, the question is asking us to find this area, right? So we just have to figure out where these two functions intersect, and you can see that they intersect like this. So, and then to do that mathematically, you just have to set these two functions equal to each other and solve for y, and you'll get an answer. So when you do that, you'll end up with like y squared is equal to 8 minus y squared, which gives you 2y squared is equal to 8, so y squared equals 4. So y is going to be equal to plus or minus 2, so or 2 and negative 2. So right there, boom, we have our boundaries. We can just plug those in, simplify, call it a day. But since we're finding the area between two curves, you also need to figure out how to set up those two equations within your integral. And this is the part that I was saying was tricky, because usually in the normal case, in the normal case, you just, in this case, like let's say it did look like this, you would just end up subtracting this blue function from the red function, right? But in this case, since we're looking at it sideways, you gotta subtract the left heavy function from the right heavy function. So instead of up and down, it's gonna be left and right. So when integrating with respect to y, you subtract the left function from the right function. So keep that in mind. Probably doesn't feel as intuitive, but try to get comfortable with it because it'll save you time. So when you do that, you should end up with a function that looks like this. So you have our lower boundary of -2, upper boundary +2 of 8 minus y squared, because this red function, that's going to be 8 minus y squared, and this blue function, that's just going to be y squared. So I'll even label those. So this is 8 minus y squared, and then this is y squared. So then setting up your integral, you should end up with something that looks like this. And then that can simplify to -2 to 2 of 8 minus 2y squared. And then from here, all we have to do is just compute it and we'll have an answer. So you can see how the math, like I was saying earlier, that the math is identical. It's just visually less intuitive. So when you run through this, you end up with 8y minus 2y cubed over 3, evaluated from -2 to 2, which equals 2 minus 2 cubed 3, minus 8 -2 minus 2 -2 cubed over 3. Simplifying again, 16 minus 16 over 3 minus -16 minus, no, plus 16 over 3. Simplifying again, should end up with 32 minus 32 over 3, which equals 96 over 3 minus 32 over 3, which just equals 64 over 3. So this would be the area between the two curves here. So the answer to this question should be C. So you can see how so this was the computationally easy but visually unintuitive approach. Then you can take the conventional route, which you'll see is more visually intuitive, but the computation is going to be like just really ugly. But I'll show you anyway in case you're hell bent on doing it that way, which is understandable. I get it. It's just I would still suggest trying to get comfortable with this because it'll save you time on an exam. Anyway, the first step is we need to rewrite these two functions where y is isolated instead of x. So you'd end up with something that looks like this. So x equals y squared. This would become y is equal to plus or minus the square root of x. Emphasis on the plus or minus, because that if you don't account for that, you're gonna end up with basically the correct answer divided by 2. So yeah, keep that in mind, since we're dealing with a square root. Similarly, in the case of x is equal to 8 minus y squared, when you isolate y, you'll end up with y squared equals 8 minus x. So y is going to be equal to plus or minus the square root of 8 minus x. And then similarly, to find the boundaries, finding the boundaries is also going to be different, because now, since we're doing it the normal conventional way of integrating along, integrating along the x-axis, the boundaries are going to be different, and you're going to come to realize that we're going to have to break this up into 2 integrals. Because you can see how when you do it that conventional way, like both of these functions are like equally level. Like there isn't an upper function and a lower function. And so you're going to end up having to integrate like this function, like the blue line from here, from like here to here, and then the red function from like here to here. And so all we'd have to do is just figure out like that intersection, and that would be like your upper boundary for the blue line and the lower boundary for the red line. You can see what I mean by like it gets fuzzy. So to do that, we can just to do that, it's the same process as the other case where you set these two functions equal to each other. So you end up with plus or minus the square root of x is equal to plus or minus the square root of 8 minus x. Square these, you should just end up back with just x is equal to 8 minus x, which gives us 2x is equal to 8, so x would be equal to 4. So, and then the next thing we have to do is we need to figure out where these two functions are equal to 0, so being along the x-axis. That's pretty simple. For the first function, it's obvious that that's going to be 0. And then in this case, it's going to be 8, because when you set these two functions equal to 0, you end up with like 0 equals plus or minus the square root of x, and then 0 equals plus or minus the square roots of 8 minus x. So when you simplify this, you just end up with 0 equals x, and then 0 equals 8 minus x, so x would be equal to 8. So now that we have all of those things, we can set up our two integrals. So the first integral, you're going to end up with the integral from 0 to 4 of plus or minus the square root of x with respect to x, plus the integral from 4 to 8 of plus or minus the square root of 8 minus x dx. And so the reason why I said that these plus or minus things were important is because when you integrate this with respect to x, the answer that you're going to get is only going to account for this side of the region and not this. And that's and the plus or minus takes care of that. Like the plus side, that takes care of this side of the line, and the minus side is going to take care of that side of the line. And so what we're going to have to do is we're going to have to end up doubling this to get the correct answer. And the double will get rid of the plus or minus and allow us to actually integrate this. And so we'd have to replace this really ugly expression with 2 times the integral of 0 to 4 square root of x dx plus integral 4 to 8 of the square root of 8 minus x dx. Now, and so from here, now you can compute this, but yeah, it's gonna be rough. So simplifying this, rewriting this, you should end up with x 1/2 integral, that just becomes 2/3 x 3/2 evaluated from 0 to 4, plus similarly here, you'd end up with 8 minus x 3/2 times 2/3 evaluated from 4 to 8. And then skipping the plugging in the boundaries thing, if you do all your algebra from here correctly, this will also simplify to 64 over 3. And so, yeah, so you can see between the two cases, computationally easy, visually unintuitive versus computationally horrible, visually intuitive. You end up at the same place, but one ended up being computationally easier. So so anyway, the answer to this question is going to be C. All right, so we have an object weighing 30 newtons, and it's suspended by a spring from the ceiling. The spring is stretched beyond its equilibrium position by 0.1 meters due to the weight of the object. So how much work is needed to return the spring to its equilibrium position? Okay, so in this question, there's a bunch of things I want to point out here. First off, we're dealing with a spring, and and the question is also asking us to find like how much work is needed to return the spring to its equilibrium position, as well as the fact that it gives us an object's weight in newtons. So we're also dealing with some sort of force here. So the three main things that we're going to be working with in this case is connecting the dots between force, work, and Hooke's law. Hooke's law because, we're dealing with a spring. So if you see on an exam like this, if you see something related to a spring, then you should immediately go to doing something related to Hooke's law. So before we do anything else, let me also write out a diagram or a visual representation of what this question is looking like here. So we have our spring here with an object weighing 30 newtons in its natural position. By the way, this is a spring. That's not an inductor. But anyway, and then it tells us that the spring is going to be stretched 0.1 meters like this. So we have like a distance delta of 0.1 meters from its natural position. And it's asking us to figure out how much work is needed to get back to this position. So now from here, I'm going to start bringing in some equations so that we can tackle this problem. And then also maybe let me make this difference in distance a little more obvious. So 30 newtons and then a distance delta of 0.1 meters. And now I'm going to bring in the equation for work. We know that generally speaking, work, that's going to be equal to a force times a distance. And then now let me also bring in Hooke's law. We know that Hooke's law gives us a relationship that tells us that force is going to be equal to some sort of spring constant times the displacement of the spring from its original position. So like how much distance did like how much did the length of the spring change after it was stretched or compressed? That's what x is going to tell us. So x is going to be a distance. And then the next thing I want to do is I want to relate force. I want to relate that with work because that's going to be important here for coming up with our final equation where we can just plug and chug stuff to get an answer. The thing with this relationship for work, this relationship only gives us we can only find work if we what is it if we knew that distance was constant. It might be easy to think like we just have to multiply 30 times zero point 0.1 and we'd have a work. But that will end up giving you the bait answer here of 3 joules, which is incorrect. Because in this case, distance is not going to be constant. And the reason distance is not going to be constant is because it's actually going to be a variable ranging between this distance delta here that I mentioned earlier. So it's going to range between like 0 and 0.1 as a variable. And since our distance is going to be a variable, we're going to have to add up all of the we're going to have to add up the work done at every single distance between 0 and 0.1. So summing up a bunch of infinitely small works into one thing. So my point is we're going to have to integrate. Going back to what an integral is conceptually of adding infinitesimally small things together, we're going to have to do this with work. So we're going to have to integrate. Now, to come up with our integral equation, I'm going to relate work and force together, force and work together. So notice how in the equation for work we have force times distance, and then we just have force here without a d attached to it. So what I'm trying to get at here is you can come to the conclusion that since work is a force over a distance, force is going to be the derivative of work with respect to distance. Because going back to what a derivative is conceptually, we know that a derivative, that's going to give you like some sort of rate of change at a specific point for a function. So force is going to be the derivative the derivative of work with respect to distance. So we can say that dw, that's going to be equal to just force times x being our variable for distance because of Hooke's law here. And so we can say that, and so from here, if we integrate this, we'll end up back here and have a work. And so now all we have to do is just replace force with something that's in terms of x. And that our answer to that is right here. We have f is equal to kx using Hooke's law. So we can replace this and we can end up with a new equation that tells us that the derivative of work is equal to kx dx. Now from here, all we have to do is just integrate this, and we'll end up back here. And so when you do that, we can finally come up with a final equation telling us that work is going to be equal to the integral of kx dx. The last thing we have to do from there is just come up with our boundaries, and that's going to be pretty simple. Like I mentioned earlier, our distance is going to be a variable ranging from 0 and 0.1, since that's the total displacement of the spring. So we can set our lower boundary to 0 and our upper boundary to 1. And then all we have to do is just figure out what k is going to be, and then we'll have our answer. And that's also pretty simple. We know that k, that's going to be our spring constant. And then in this case, so instead of, I mentioned like the bait answer would have been just to plug in 30 and 0.1 into this equation, and you'll get your work. But in reality, we're going to have to use these values and plug it into Hooke's law instead, and that will allow us to solve for k. So we know here that we have 30 newtons, so we can plug that in for F here, and we have a displacement of 0.1 meters there, so we can plug that in for X, and so we'd end up with 30 is equal to k times 0.1. Moving things around a little bit, you end up with k is equal to 30 divided by 0.1, so k is going to be equal to 300. Then we can plug that in for k, and you end up with work is equal to the integral from 0 to 0.1 of 300x with respect to x. Evaluating this integral, you should end up with 150x squared evaluated from 0 to 0.1. Plugging in the boundaries, you end up with 150 times 0.1 squared minus 150 times 0 squared, which gives us 150 times 0.01 minus 0, which just gives us 1.5 joules. And then this would be our work. And so this would be the answer to this question. So matching up with the answer choices, the answer would be A. All right, what is the angle between the vectors A and B? So A is equal to 3i, B is equal to negative I minus root 2j plus k. So since we're dealing with vectors here and it's asking us to find the angle between those two vectors, we can do that by deriving some equations from relationships between vectors and trigonometric functions. So the two relationships that I'm going to bring in for this is going to be related to sine and cosine. So recall that we know that sine theta, that's going to be equal to the magnitude of the cross product between two vectors. Since we're dealing with A and B here, I'll just use A and B. So the magnitude of the cross product between A crossed with B divided by the magnitude of A times the magnitude of B. And then we know that cosine of theta, that's going to be equal to the dot product between A and B divided by the magnitude of A times the magnitude of B. And then from here we can isolate theta and find the angle. So in the case of in the sine relationship, we can say that theta, that would be equal to the sine inverse of this blob over here. And then theta would be equal to the cosine inverse of this blob over here. So writing that out, you'd end up with sine inverse of magnitude A cross B over A, magnitude A times magnitude B. And then theta is equal to cosine of inverse over A dot B over magnitude A times magnitude B. Me personally, I would much rather use this relationship for this question than this one because we're dealing with a dot product instead of a cross product. Because cross products are a lot more computationally intensive than dot products. So for this question, I'm going to use the cosine relationship. So the next thing I'm going to do is I'm going to rewrite the vectors given to us in a more conventional notation to make it easier to do the computation. Well, I mean, I guess it doesn't really matter, but we know that like in the equation version of a vector, we know that a vector v, that would be equal to like ai plus bj plus ck or something. So in this case, a and then in its traditional form, this would mean that the vector would be equal to this, where you have a, b, and c. And then in the case of a and b, you can see that a is actually going to be equal to 3i plus 0j plus 0k, and then b is given to us as negative I plus, or minus root 2j plus k. So in traditional notation, a would end up being equal to 3, 0, 0, and then b would be equal to negative 1, negative square root of 2, and then 1. Now, all we have to do is just take some dot products and some magnitudes and stuff, and and then plug it into this expression over here, and we'll have an answer. So recall that we know a dot product between two vectors, so let's just say a dotted with b, that's going to be equal to the I values of both vectors multiplied together plus the j values multiplied together plus the k values multiplied together. So, and then in traditional notation it would be this times this plus this times this plus this times this. So when you write that out, a dotted with b is going to end up being equal to 3 times negative 1, well that's a positive 1, 3 times negative 1 plus 0 times the negative square root of 2 plus 0 times 1, which just gives us negative 3 plus 0 plus 0. So a dotted with b is going to be equal to negative 3. Now we also need to find the magnitudes of these respective vectors. And we know that a magnitude of a vector, let's just say magnitude v, that's going to be equal to I squared plus j squared plus k squared, and then the square root of that. And that will allow us to convert a vector into a scalar. So magnitude A is going to be equal to, that's going to be equal to 3 squared plus 0 squared plus 0 squared, square root of that, gives us 9, square root of 9, which is 3. So the magnitude of A would be 3. Magnitude of B, that's going to be equal to negative 1 squared plus square root 2 squared, or the negative of that, plus 1 squared. Simplifying this, you end up with 1 plus 2 plus 1 in a square root, which gives us root 4, which gives us 2. So now that we have all those values, we can plug it into this expression and solve for theta. So in that case, we can write that here. We know that theta, that's going to be equal to the cosine inverse of, what is it? Where's our dot product? Our dot product is over here. Oh, wait, no. Yeah. Is that it? Wait. Yeah, it is. Okay. Negative 3 divided by 3 times 2, which gives us the cosine inverse of negative 1/2. So then, recall that on your on a unit circle, this would be equal to, that would be equal to, I think, negative 60 degrees. Or no, well, that would be in degrees. In radians, that would be equal to 5 pi over 6, I believe. Because yeah, if you remember your unit circle, since we have a negative here. Wait, no. I have to think back to. I gotta hold on. Let me pull up a unit circle real quick. Yeah, on an actual exam, try to memorize your unit circle. I don't think it's been a while. Okay, cosine inverse of negative 1/2. That's going to be that's gonna be either. Wait a minute. What was that again? I don't. This is my moment of shame. Okay, I figured it out. I finally the knowledge came back to me. It's equal to the cosine inverse of negative 1/2. That's going to be equal to 120 degrees, which that becomes 2 pi over 3. So matching that up with the answer choices, the answer to this question is going to be A. Yeah, sorry about that little brain fart. But yeah, definitely try to memorize your unit circle in an actual exam. Alright, so what is the area of the triangle with the given vertices? Okay, so we're given vertices, and it's asking us to find the area. So because of that, we're going to have to come up with some vectors, and then take a cross product between those vectors and divide it by 2, and we'll have an answer. This isn't going to be the typical case of like when you're finding the area of a triangle where you just like take 1/2 base times height and call it a day. We're gonna be dealing with vectors instead. So recall that in that case, the general formula for that we know is going to be that area is going to be equal to 1/2 of the magnitude of the cross product between two vectors, let's just say u and v. So now we have to come up with our vectors because we're given vertices here instead of actual vectors. And so the way to do that, let me label the 3 vertices given to us. So we have A, we have B, and we have C. And to come up with the vectors, we want to come up with 2 vectors that have the same starting point. And the reason we want to do that is using a visual representation. It's asking us to find a triangle, so we want to come up with a situation where we have vectors branching out like this. So we have like one vector going out that way and another one going out like this. And so with that, you end up with a triangle, this being the triangle. So I'm going to use A. I'm going to use A as our starting point because that's the most simple one. It's just 1, 1, 1. So we can say that our first vector is going to be vector AB, and that's going to be the distance between the 2 points, so B minus A. So it would end up being B minus A. And then our other vector, vector AC, that's going to be C minus A. And so with that in mind, that this is going to end up looking like this. So AB is going to be equal to, or wait, let me move this down a little bit. It's going to end up being this. So if I move this down here, over here, it's going to end up looking like, 5, 1, negative 2, minus 1, 1, 1. And that's going to give us a vector of 4, 0, and negative 3, I believe, if I didn't make any mistakes. Okay, yeah, we're good. I did not make any mistakes, so that's good. Oh, I did make a mistake. I'm an idiot. This is the wrong point. This is supposed to be this is supposed to be 3, -1, 2. Okay, so now our new vector is going to look like 2, -2, and 1. And then all I did here, if you're not sure, is I just took the difference between each of these corresponding things. So 3 minus 1, -1 minus 1, and then 2 minus 1, and then you end up with this vector. Using that same logic, you do the same thing for the other point. So now it's 5, 1, -2, minus 1, 1, 1, and you should end up with a vector that looks like 4, 0, and -3. So if, okay, yeah, everything here checks out. I think I did everything right. I don't think I made any stupid mistakes. Okay, yeah, so these are going to be our new vectors. So the area of our triangle here is going to be this. So we're going to say that area is now going to be equal to 1/2 times the magnitude of the cross product between AB and AC. Now, generally speaking, when you take a cross product, depending on the order, you're gonna if you flip it, you're gonna end up with the same cross product, but the sign's flipped. But since we're taking a magnitude, we don't have to worry about that because the magnitude is going to correct that. So you can either take the cross product between AB and AC, or the other way around, where you have AC here and AB there, and you'll end up at the same place once you take the magnitude. So here it doesn't matter, but if in other cases where it just wants a cross product, it does matter. So keep that in mind. But anyway, let's set up our cross product apparatus thing. So we know that the cross product between U and V, that's going to end up looking something like this, where you have your values here, like here, 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 or whatever, with like I, J, K, and then you'd split this up into 3 matrices and take the determinant of those, and you'll end up with like, so like something like here, I minus minus some other matrix here, J, plus another one here, K. And then when you take the determinant of these 3 things, you'll end up with 3 scalars, and then that's going to be used to generate your new vector from your cross product. Because recall that a cross product, unlike a dot product, is going to give you a vector instead of a scalar. And that's also why we have to take the magnitude of it to turn it into a scalar, since an area is a scalar. So applying that to the vectors we have here, the cross product here, this is going to turn into this, where we have 2, -2, 1, 4, 0, and -3, I, J, K. And then this is going to turn into, to set up our first matrix, what you're going to do is, for each of these corresponding letters, you're going to use the other 2 columns. So the first matrix is going to be I, so we're going to skip this column, and then make a matrix using these 2 columns instead. So you're going to end up with something that looks like -2, 1, 0, and -3 times I, minus, for J, we're going to skip this column and use these 2 columns instead. So you're going to end up with 2, 1, 4, and -3 times J, plus K, skipping K here, we're going to use these 2 columns instead, and you're going to end up with 2, -2, 4, and 0 times K. Then all we have to do is take these determinants and then split up the equation into vector form. And so that's going to end up looking like, to take a determinant, we're going to multiply these 2 values and then subtract it from these 2 values multiplied together. So you want to multiply diagonally and take the difference. So that's going to end up looking like this, where you end up with -2 times -3 minus 0 times 1 times I, minus 2 times -3 minus 4 times 1 times J, plus 2 times 0 minus -2 times 4 times K. And then this is going to be, and then simplifying this, we're going to end up with a vector in equation form. So after you simplify this, you should end up with 6 minus 0 times I, minus -6 minus 4 times J, plus 0 plus 8 times K. And so then this is going to become 6I plus 10J plus 8K, I believe. I think, yes. Okay, yeah. And so then this is the vector in equation form, and then turning it back into its coordinate form, this is going to turn into 6, 10, and 8. And so this is going to be the vector that we came up with using the cross product. And so then going back to this equation over here, all we have to do is take the magnitude of our vector, and that was an accident. Okay, there we go. And so in order to do that, the magnitude, that's going to be equal to, I'll put it over here. Let me rewrite the formula over here so we know that area is equal to 1/2 AB cross AC. So the magnitude of AB cross AC, that's going to be equal to the square root of the I value squared plus the J value squared plus the K value squared. So that's going to end up looking like 6 squared plus 10 squared plus 8 squared. And then since all of the values we're working with are positive, it doesn't matter here. But if you're dealing with a negative number, make sure you put it in parentheses because you want to make sure you have a positive number at the end of this entire thing. And so then this is going to simplify to 36 plus 100 plus 64, square root of that, which equals, I think, what is it? Square root of 200? Yeah, square root of 200. And then we have to, looking at the answer choices, that doesn't match up with any of the things here. So we're going to have to split this up and say that this is going to be equal to the square root of 2 times the square root of 100, which is going to equal 10 root 2. And then for the area, we have to divide this by 2. So dividing this by 2, you should end up with 5 root 2. And then this is going to be our area. So matching that up with the answer choices here, the answer to this question would be D. Okay, so, all right, we're given a region R, and it's bounded by y equals x squared and y equals 2 and the y-axis. So what is the volume of the solid obtained by revolving R around the y-axis? So first off, let's draw out what the region we're dealing with is going to be in 2 dimensions. So we have our plane here, and it tells us that it's being rotated around, it's bounded by y is equal to x squared, which let's just say it's going to look something like this. And then y equals 2, so putting like 2 here, this, and then the y-axis, so the y-axis. And so our region is going to end up being somewhere, it's going to be like this, like half of this, it's going to be like this. Ignoring this side, it's going to be this. And so then we just have to revolve this around the y-axis, so we're going to have to revolve it like this. And that will give us the volume of the solid. And so there are 2 ways that we can go about this. You can either use since this is obviously a disk washer or shell method kind of question, you can use either of the approaches. You can get to the right answer using either of the approaches. You just have to make sure that you set up everything properly. So the first thing I want to point out is recall that the disk and washer method, that's going to take slices, that's going to add up slices of your volume thing. Like it's going to add up slices perpendicular to the axis of rotation. So since we're using the y-axis as the axis of rotation, the disk and washer method is going to take slices horizontally like this. Now, if we were to use the shell method uses it takes slices parallel to the axis of rotation. So the slices would end up looking something like this. And that's going to be important because that's useful to help determine which variable you want to integrate with respect to. Using the disk and washer method, since we want, how should I put it? We're going to have to, if we're going to use the disk and washer method, we're going to have to, actually, you know what? No, let me just write out the formulas first, and then we can go from there. So we know that for disk and washer, that's going to be equal to v is equal to pi times the integral from a to b, that's a 0, of, that's going to be equal to the integral from a to b of, like, I guess your variables, your function squared. So let's just say r squared with respect to x or y. And then shell method, that tells us that the volume is going to be equal to 2 pi times the integral from a to b of, like, let's just say x times, like, r of x with respect to x or something. So anyway, for this question, if we want to use the disk and washer method, we're going to have to change our equations and rewrite them in terms of x. The reason why is because since our axis of rotation is along the y-axis, and the slices are perpendicular, we're going to have to integrate with respect to y instead. So using the disk and washer method, you end up with v is going to equal to pi times our boundaries times this expression reworked in terms of y. So this is going to end up being like y equals x squared. We're going to have to turn this into x equals the square root of y, and then take an integral. And then because the slices are looking like this line right here is going to end up being an upper boundary. And so instead of putting that into this, we're going to end up putting it here. And so it's going to end up looking like this, where you have 0 to 2 of the square root of y squared with respect to y. And then this is going to turn into pi times 0 to 2 of y dy, which equals y squared over 2. Wait, I forgot a pi. So pi times y squared over 2, evaluated from 0 to 2. And then this is going to become, this is just going to become pi times 4 over 2, which just equals 2 pi. And so this is how you get the volume using the disk and washer method. And so in this case, the answer would be B. Now I'll show you how to do it using the shell method. Since the shell method takes, since it takes slices parallel to the, to the axis of rotation, in this case, we won't have to do what we did with the disk washer method, because basically the variable that you integrate with respect to, it needs to be the variable that's perpendicular to your slices. And so in this case, the x-axis is going to be perpendicular to the slices. And so in this case, we can just integrate with respect to x. And so doing that, you end up with v. And so we can keep these functions as is. But it is going to be a little bit trickier, because if we're going to use the shell method to do this, we're going to have to account for the difference between this and this, because we're integrating or taking a volume between two functions. And so our shell method formula is going to end up looking like 2 pi times the integral of x times 2 minus x squared with respect to x. And another thing is the boundaries that we're going to be using are also going to be a little bit trickier, because we're integrating along this axis and we want to go up to this point. So like we only want to integrate between here and here, but this value, that's not going to be 2, unlike the disk and washer method situation. So in order to find that upper boundary, we're going to have to set these two things equal to each other and find our upper boundary. So we can say, well, we have y equals x squared, and then y equals 2. So x squared would be equal to 2. So x would end up being equal to the square root of 2. And so this would end up being our upper boundary instead of 2. And so then plugging that in here, you end up with 0 to the square root of 2. And so you can probably see already here, like, the disk and washer method for this question is going to be easier computationally after you change the functions variables, versus the shell method. You can see it's a lot more convoluted here. So integrating this, there's two ways you can do it. You can either distribute this into here and then just do a bunch of reverse power rule, or you can keep it separated like this and just do a u sub. I'll just distribute it to avoid having to do the u subs. You end up with you can do either one, whichever one you're more comfortable with. 2x minus x cubed, 0 to root 2, 2 pi dx. This is going to equal 2 pi times x squared minus x to the 4th over 4, evaluated from 0 to root 2, which is going to equal 2 pi 2 minus 4 over 4, which equals 2 pi times 1, which is equals 2 pi. So yeah, that's how you get the answer using either method. You can use whichever one you're more comfortable with. Like if you don't like having to rewrite functions in terms of like new variables like we did with the disk washer method, then you can end up doing it this way. Personally, I would prefer to do the disk and washer method because the actual integration ends up being easier. But yeah, so that's how you would do this problem. Okay, so in this problem, we're given a solid with a semicircular base of radius 3, and it tells us that the cross sections perpendicular to the base and parallel to the straight edge of the semicircle are going to be squares. So what would the volume of the solid be? So the first thing I'm going to do is I'm going to write some stuff on this diagram to make things easier to see. So it tells us here that the cross sections perpendicular to the base and parallel to the straight edge of the semicircle are squares. So you can see how it's clearly parallel to the straight edge because this is going to be the straight edge in question, and you can see how this square here is parallel. And then you can also more clearly see that these squares are perpendicular because they're standing straight up. So like I can put a line here and here, and you'll end up with a right angle here. So that's how these cross-sectional areas end up being perpendicular. And then I'm also going to draw a top-down view of our solid, or the base of it, so to get a better, a different view of what we're working with here. So we have our graph here with our x and y axis, and then we have our semicircle, which looks something like this. And then, or let me use a thicker line to make it more obvious. So we have like, yeah. So then we have our semicircle that looks something like this. And then we have the cross-sectional areas that when you look at it from the top down, you should end up with lines that look something like this. And so yeah, this is going to represent our top-down view. And then we can also, and it has a radius of 3, which I'll put like that. And so basically the goal of what we want to do here to find the volume is we want to find the areas, the individual areas of each of these cross-sectional areas, and then add them all together. So like these areas, we want to find the area of this square as well as this square, and then like every other possible square in between up until this square over here, and add them all together. And so for that, we're going to have to use an integral, because if you go back to what an integral is conceptually, where you're adding up an infinitesimally small amount of slices together, that applies here, except we're adding cross-sectional areas instead of like just individual numbers. And so we can come up with a general formula for this that tells us that the volume is going to be equal to the integral from a to b of the cross-sectional area. Like so, and then I'll just put y here just so we have a differential. And then to represent the cross-sectional area, we need to come up with a equation that represents that. So in this question, it tells us that the cross-sections are going to be squares. As you can see here, cross-sections perpendicular to the base and parallel to the straight edge of the semicircle are squares. And so for that, for the cross-sectional area, we can just use the formula to find the area of a square. So we know that with a square, you'd have like sides that are equal to each other, so s, 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 and s. So the area in this case should be equal to s times s, or just s squared. And so then we can plug this in. We can plug this into this equation, and we'll end up with a new expression that looks like v is going to be equal to the integral from a to b of s squared, like so. The problem is we need to figure out what s is actually going to be equal to, because s, that's not a number. We don't know what that is. All this does is give us a relationship of how to get the area from some length s. But the kicker is, in this case, s is not going to be a constant. It's going to be a function that involves a variable. And the reason why is because since we're adding up all of these cross-sectional areas, notice how the length of them is not going to be the same for all of them. So like in this case, this square's length is shorter than this square's length. And so we're going to have to use a function to represent all of these squares, and then plug that in for s instead of a specific number. And so in order to come up with that function, I'm going to use the fact that it gives us a radius here. we can use this to come up with the function. So we know, generally speaking, that the general formula for a circle is going to be like x squared plus y squared is equal to r squared, where r is your radius. And we know that in this case, the radius is going to be 3. So we can plug that in for r. You'd end up with x squared plus y squared is going to be equal to 3 squared, which equals 9. So this would represent like a circle with a radius 3. The next thing we have to do is we want a function. We want a function in terms of a single variable. And so we want to either try to isolate x or y. But in this case, I'm going to isolate y, and I'll explain why. So if we go back to let's go back to like what the formula for, or not the formula, but the way you would find a volume using the disk or washer method. If you remember, the disk and washer method, like that takes slices. Like your slices for your part are going to be perpendicular to your axis of rotation. So in this case, the y-axis. Notice how, and so that also applies to these kind of problems too. Notice how these slices are perpendicular to the y-axis. And so because of that, we're going to want to integrate along the y-axis. If this semicircle was like this or something, with the slices being like this, then we'd want to integrate along the x-axis. And so yeah, you want to integrate along the axis that's perpendicular to your cross-sectional area. So I'm going to rewrite this function in terms of y. And so when you do that, you should end up with x squared is equal to 9 minus y squared, which is going to turn into x is equal to plus or minus the square root of 9 minus y squared. Also, note that this plus or minus, that's going to be important because if we didn't include that plus or minus, that would only account for half of our circle, but we want the entire thing, I guess. And so, because basically, if you include only the plus case, then it would only include this side of the circle. And then if you only included the minus case, then it would only include this side of the circle. But the circle has this, so that's why we need the plus or minus. But we can't integrate that, so we're going to have to replace that plus or minus with something that can compensate and represent both of these lengths. Since we know that the positive or the negative side on their own only accounts for half of this curve thing, we can replace the plus or minus with a 2, and we can say that x is going to actually be equal to 2 times the square root of 9 minus y squared, like this. And so this is going to be the function that represents the length of each of these squares. And so we can say that this is going to be equal to s. And so we can plug this thing in for s and then integrate. And so we can see that v is going to be equal to the integral of 2 minus the square root of 9 minus y squared with respect to y. As for the boundaries of integration, that's going to be pretty simple. We're dealing with a semicircle here. And so we know that the straight edge of the semicircle is going to be along the x-axis. So that's going to be equal to y is equal to 0. And we know that the radius of our circle is 3. So that would be y is equal to 3 here. And so from here, you can see that our integration boundaries are going to be from 0 to 3. Now, if we were dealing with a full circle like this, then the lower boundary would be equal to -3 because it would be down here. And so yeah, so this is going to be our final integral, and all we have to do is just evaluate this and we'll have an answer. So this should turn into the integral from 0 to 3 of 4 times 9 minus y squared with respect to y, which then this equals, and then this is going to equal 0 to 3 of 36 minus 4y squared, which equals 36y minus 4y cubed over 3, evaluated from 0 to 3, which equals 36 times 3 minus 3 cubed over 3, which equals 108 minus 36, which is going to equal 72. And so this is going to be the volume of this solid. And so matching that up with the answer choices, the answer is going to be B. Okay, in this question, it's asking us to find the surface area of the surface generated when the curve y equals x cubed over 3 is rotated about the x-axis from 0 to 1. So to find a surface area in questions like this, there's a formula for that. We know that for surface area, we know that SA is going to be equal to 2 pi times the integral from a to b of the function, or I guess the function that represents the curve. So let's just, in this case, let's say y, times the square root of 1 plus the derivative of y squared with respect to that variable. So in this case, it would be x. So we know that y is going to be equal to x cubed over 3. And so taking that derivative to find y prime, we can find that y prime is going to be equal to x cubed. And then we know that our boundaries are going to be 0 and 1 because they're written over here. So we can plug that straight into the formula, and you end up with an integral that looks like the surface area is going to be equal to the to 2 pi times the integral from 0 to 1 of x cubed over 3 times the square root of 1 plus x squared with respect to x. And so then this x squared, that's just going to become x to the 4th. And then from there, we can just integrate this. And to find this integral, we're going to have to use a u sub. So in this case, we're going to have to, we want to cancel out this variable here and make this term more simple to make the integration like not as ugly. So I'm going to set my u equal to 1 plus x to the 4th. So du is going to be equal to 4x cubed with respect to x. And so dx is going to end up being equal to du over 4x cubed. And then adjusting our boundaries, 1 plus 1 to the 4th, that's going to be 2. And then 1 plus 0 is just going to be 1. So our new integral is going to end up looking like this, where we have the integral 2 pi times the integral from 1 to 2 of, and then also I'm also going to take out this 3 here. So actually this we can make this look like 2 pi over 3 times the integral from 1 to 2 of x cubed times the square root of u du over 4x cubed. And then these x's are going to cancel, so then we can end up with this. And then we can also take this 4 out as well. For this question, I'm taking out all the constants as soon as I can, because it'll make the final computation when we plug in the boundaries a little less tedious. So you should end up with 2 pi over 12 times the integral from 1 to 2 of the square root of u with respect to u. And then this is going to give us 2 pi over 12 times 2/3 u to the 3/2 evaluated from 1 to 2. Simplifying these fractions a little bit, we should end up with 4 pi over 36. That equals pi over 9, I think, times u to the 3/2 evaluated from 2 to 1, which gives us pi over 9 times 2 root 2 minus 1, I believe. Yeah. Okay, yeah. So, and then rewriting this to look like the answer choices, this is going to become pi times 2 root 2 minus 1, all divided by 9. So this is going to be our final answer. And so matching that up with the answer choices, the answer is going to be B. Alright, which one of the following integrals equals the arc length of the curve given to us here, ranging from 1 to 2? So recall that to find the arc length of a function ranging from some boundaries can be found by using a known formula, that being that we know that arc length, that's going to be equal to, let's just say L is going to be equal to the integral from a to b of the square root of 1 plus the derivative of the given function squared. So let's just say y prime squared. Or, well, it's an equation in terms of x, so I'll write the derivative with respect to x. So dy dx squared in a square root, and then integrate this with respect to x. And so we can plug in the known values into this and come up with an equation to find the arc length. So we know that the boundaries are going to be 1 and 2 because it's given to us here. And so the length is going to be equal to the integral from 1 to 2. And then all we have to do from here is just find the derivative of this. So we know that the derivative of that, so we have y here, it's going to be equal to x cubed plus 1. So dy dx is going to be equal to 3x squared. And so then you'd end up with 1 plus 3x squared squared. And then simplifying this, you should end up with 1 to 2 of 9x to the fourth plus 1. And so yeah, so this is going to be our arc length. So matching that up with the answer choices here, the answer is going to be B. Okay, which one of the following integrals equals the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals x about the line y equals 3? So before I proceed anywhere else in this problem, I'm going to highlight in red this part right here, this line x equals 3. This might screw some people up because we're actually rotating about a line that's not the x or y axis. And so we're going to have to do some additional steps to account for that shift and to come up with our integration formula. So that's going to make things a little bit more tricky. So recall that the first thing we do is let me draw out what we're working with here. So we have our two-dimensional plane here of x and y. And we know that the region is bounded by y equals x squared, so that's going to look something like this, and it's bounded by y equals x, which looks something like this, and it's rotated about the line x equals 3, so it's rotated about this line. This is going to be our axis of rotation rather than this line, or rather than the y-axis, and so. Make sure you stay on top of that because that we're gonna have to account for that shift. So I'd say that the easiest way to go about solving this problem would be by using the shell method. Not to mention the fact that each of the answer choices resemble something that like an integral that was found by using the shell method. I know this because there's a 2 pi in each of these answers. Whereas if you go back to the formula for a disk and washer method, that only has a pi in it. And so yeah, we're gonna have to use the shell method for that. So you might remember the formula for the shell method being that v is equal to the integral from a to b of 2 pi times x times your region function x dx or something, right? The thing is, this is going to be a little bit different. We're going to have to go back to the more generalized form of the shell method formula because this formula is actually it's a simplified form of the shell method that comes from a more generalized equation, because if you remember the shell method formula, it comes from the formula to find the volume of a cylinder. Recall that is going to be equal to not a cylinder, but the more generalized form. Let me rephrase. No, the more generalized form of shell method is where you multiply 2 pi times a radius and a height, where the radius and your height is going to be represented by some sort of function. And generally speaking, the radius is usually represented by x, and then your height function ends up just being the region, because the height changes depending on where along your region you are. And then the reason that it's x is because usually you're only rotating along an axis, so you don't have to account for a shift. But because we're dealing with the shift of x is equal to 3, we're actually going to have to replace this x with a 3 minus x to account for that compensation. It's similar to how, like, when you have a function, it's similar to when you have a function like this where, like, let's say you have, like, it's similar to how when you want to shift the function left or right, you have to do a shift like that where you do, like, 3 minus x or something. Like, you can see it in each of the answers here. And so for that, we're going to have to replace this x with 3 minus x. And so we're going to end up with v is going to be equal to the integral from a to b of 2 pi times 3 minus x times some function r of x with respect to x. And so, or I guess a better way to look at it is like this 3 minus x thing, this basically makes it so that you have to do, I guess, 3 extra of something to achieve the same thing. And so that would result in a shift on a graph. And then the function r of x, that's just going to be our region here. And so that's just going to be as simple as subtracting the lower function from the upper function. And so that's going to end up looking like this, where you have the integral from a to b of 2 pi 3 minus x times x minus x squared. And then for our boundaries of integration, that's going to be pretty simple. That's just a matter of figuring out where these 2 points intersect. And so we can do that by setting these two functions equal to each other. And so we can say that since y equals x squared and y equals x, then x equals x squared. And so then you simplify this and you end up with 1 is equal to x. And so that would end up being our upper boundary here. And then the lower boundary is just going to be the origin. And so then this would end up being from 0 to 1. And so this would be the integral that represents the volume of this. And so then we can just match this up with the answer choices. Thankfully, we don't have to actually evaluate this integral, which is nice. So matching this up with the answer choices, I believe this matches up with D. Okay, so in this question we have a thin metal bar of length 2 meters which pivots around a hinge on the floor. And at x meters away from the hinge, the bar has a density of rho of x is equal to 10 plus x kilograms per meter. Assuming gravitational acceleration g is equal to 10 meters per second squared, how much work against gravity is required to pivot the bar upright from a horizontal position? Okay, so there's 3 things that I want to bring up in this question. The first thing is, well, the question is asking us to compute a work because it tells us how much work against gravity. And then the question also gives us a density here of density rho of x. And then it also gives us a gravitational acceleration of g is equal to 10 meters per second squared. So with that in mind, I'm going to bring up 3 things, that being density, force, and work. And I'm going to establish a relationship between those 3 things to come up with an equation that we can use to solve this problem. So the first thing I'm going to do is I'm going to bring up the general relationship for density. You know that generally speaking, density, rho, is going to be equal to mass divided by volume. But in this question, we're dealing with a thin metal bar. And so that means that we can assume that the width of this bar over here is going to be negligible. And so we could end up approximating the bar as just, we can approximate the bar's volume as just a singular length. And so we can say that rho is actually going to be equal to mass over length. And then the next thing I'm going to do is I'm going to bring up force. We know that force is going to be equal to mass times acceleration. And then we know that work is generally going to be force times distance. The next thing we have to do is we need to establish a relationship between density and force. And the reason why is because the question doesn't give us a mass. And so we're going to have to figure out how to plug in something for m here to give us a mass. But what we do know is that there is a mass in the relationship for density. And so what we can do instead is we can substitute density into the force equation and come up with a new force equation that incorporates density into it. So we can say that force is going to be equal to m over L times some acceleration. Next thing we have to do is we need to cancel out this length so that we can have this equation be equal to this while still incorporating density. And so we can just attach another L here to cancel out these 2 things. And so from here, now we have a density added into the force equation while still being equal to our original force relationship here. And so then we can substitute rho in for m over L, and we can say that force is actually going to be equal to rho times L times acceleration. The next thing we have to do is, now that we have this adjusted force relationship, we need to relate it to work here. So we know that work, that's going to be force times distance. The problem is this relationship, that only holds assuming that the distance is constant and assuming the question is asking us to find a work from a preset distance. The problem with this question though is the distance that we're going to be working with is going to be a variable. It's not going to be the same. It's not going to be constant because the work is not going to be uniform. The amount of work needed to push this bar back to its vertical position, it's going to change depending on where along this path the bar is at any given moment. And so that's why our distance is going to be a variable. And it's going to be a variable ranging along the length of the bar. So it's going to be ranging somewhere between somewhere along the 2 meter length given to us. And I'll revisit this later when we get to our final equation. And so because of that, we're going to have to add up all of the works along this path to get the total work to complete this process of bringing the bar back up. And so what I'm getting at is we're going to have to take an integral. And then the next thing I want to do is I also want to make it more clear, I'm also going to relate it to force. If you take the derivative of this relationship with respect to distance, you'll just end up with dw is going to be equal to force. Because treating this as a variable and then taking a derivative with respect to that variable, you just end up with force, right? And so from here, we can conclude that force, that force is going to be a derivative of work with respect to distance. And so we can say that knowing that we have a relationship of force here as well, that being rho length acceleration, we can say that dw is going to be equal to rho times length times acceleration. And then, so from here, instead of finding work by using this relationship, we can actually find work by just integrating this. And so we're going to end up with a final work equation that tells us that work is going to be equal to the integral of this thing. So rho length A with respect to some distance. And then I'm going to use x for that because that's going to be our distance variable going off of here. And then the next thing we have to do is we just need to plug in the values that we know. So we know we were given, and so actually no, yeah, we just have to plug in the things we know and then also set up our integration boundaries. So I mentioned earlier that the distance that we're going to be working with is going to be a distance that's ranging somewhere along the length of the bar. And so that would mean that the distance could be anywhere from 0 to 2 meters. And so our work boundaries are going to end up being that work is going to be equal to the integral from 0 to 2. And then I mentioned that the distance is going to be a variable, and so we can plug in x for length here. And so we can and then plug in what we know for density and acceleration. So we know that density is going to be 10 plus x. So we can put in 10 plus x here. And then we know that acceleration is going to be g, which is equal to 10. So we can put in a 10 here. And then we know that our length is going to be our distance, which is a variable, so x, with respect to x. So now we have a completed equation, and all we have to do is just compute this, and we'll have it work. So the first thing I'm going to do from here is take out this 10 because it's a constant. So we have a new thing that looks like this, simplified, where we have work is equal to 10 times the integral from 0 to 2 of 10x plus x squared. And then I also distributed this x into this term. And then from here, this is going to become 10 times 5x squared plus x cubed over 3, evaluated from 0 to 2. Plugging in the boundaries, you should end up with 10 times 5 squared plus 2 cubed over 3 minus 0 because the lower boundary is just 0. And so then this is going to become 10 times 20 plus 8 over 3, which is going to equal 200 plus 80 over 3, which is ultimately going to equal 680 over 3 joules. And so matching that up with our answer choices, the work for this question is going to be equal to E.